Good morning, students. Today we are going to see about chapter 11, problem number 26. Ultraviolet light of wavelength 2271 Armstrong units from 100-watt mercury source irradiates a photocell made of molybdenum metal. If the stopping potential is 1.3 volt, estimate the phi naught of the metal. How would the photocell respond to a high intensity 10 to the power of 5 Weber meter inverse squared red light of wavelength 6328 Armstrong unit produced by the helium neon laser? The lambda given is 2271 Armstrong units. Convert it into meter. Multiply it with 10 to the power of minus 10. Then V naught is equal to 1.3 volt. Formula phi naught is equal to h nu minus E V naught. Substitute the value of E as C by lambda. Nu is equal to C by lambda. So hc by lambda minus E V naught. Substitute the values for h, c, lambda, E and V naught. You will get the answer as 6.68 into 10 to the power of minus 19 joules. So convert it into electron volt. EV means you have to divide by 1.6 into 10 to the power of minus 19. You will get the answer as 4.2 electron volt. Threshold wavelength lambda naught. We have to find it. Lambda naught is equal to hc by phi naught. This is the formula. Then substitute the values of hc and phi naught. You will get the answer as 2.977 into 10 to the power of minus 7 meter. The lambda naught is equal to, then convert this meter into Armstrong units, so that it will be 2977 Armstrong units. So the given wavelength is 632 lambda is 6328 Armstrong units. Now the threshold wavelength will be 2977 Armstrong units. This is lesser. So the lesser photocell will not respond to the red light produced by helium neon laser. However intensity it may be. However intense it may be. Then we can go for the next sum, problem number 27. Monochromatic radiation of wavelength 640.2 nanometer. 1 nanometer is equal to 10 to the power of minus 9 meter from a neon lamp irradiates photosensitive material made of cesium or tungsten. The stopping voltage is measured to be 0.54 volts. The source is replaced by an ion source and its radiation wavelength will be 4 to 7.2 nanometer. Line irradiates the same photocell. Predict the new stopping potential. The first wavelength will be noted as lambda 640.2 nanometer. Convert it into meter, and then V naught stopping potential and EH values are given. The formula can be taken as EV naught is equal to h nu minus phi naught. Then phi naught is equal to hc divided by lambda. Nu, substitute the value of nu hc divided by lambda minus EV naught. Bring this EV naught to this side. So let's substitute the values hc, lambda and EV naught. You will get the answer as 2.229 into 10 to the power of minus 19 joules. Then divided by 1.6 into 10 to the power of minus 19 to convert it into electron volts. So that the answer will be 1.39 electron volt. Wavelength of radiation from ion source lambda dash will be 4 to 7.2 nanometer. Convert it into meter. Then taking the new stopping potential as V naught dash, E V naught dash is equal to hc divided by lambda dash minus phi naught. This is the formula. Substitute the values 6.6 into 10 to the power of minus 3, 34 into 3 into 10 to the power of 8, and then lambda dash value and then phi naught value. You will get the answer as 2.401 into 10 to the power of minus 19 joules. Convert it into electron volts. So this is the new stopping potential. Voltage we get is 1.5 electron volt. Then we can go for the next sum. A mercury lamp is a convenient source for studying frequency dependence of photoelectric effect, since it gives a number of spectral lines ranging from the ultraviolet to red end of the visible spectrum. In our experiment with rubidium photocell, the following lines from mercury source. So the lambda value wavelength values, 5 wavelength values are given, lambda 1, lambda 2, lambda 3, lambda 4, lambda 5, and their stopping potentials V1, V2, V3, V4, V5. Determine the value of Planck constant H, the threshold frequency, and work function for the material. So we will have the formula as E V naught is equal to H nu minus phi naught. V naught is equal to, bring this E to this side, right hand side, H by E into nu minus phi naught divided by E. Mark this as equation 1. So V naught is proportional to nu. What is nu? Nu is equal to C by lambda. So we can find the wavelength, for each wavelength we can find the frequencies. Nu 1 is equal to C by lambda 1 is equal to, substitute the value of C and then the lambda 1 value, you will get the answers 8.219 into 10 to the power of 14 hertz. Similarly, for various wavelengths, we have to find the frequencies nu 2, nu 3, nu 4, nu 5. So 5 frequencies we got. Using these frequencies, draw a graph on x-axis nu, taking x-axis, taking nu in x-axis and volts in y-axis. If we draw a graph, means it will be a straight line as shown in the diagram. So what will be the threshold frequency? The threshold frequency is equal to 5 into 10 to the power of 14 hertz. Here, if we see the remaining wavelengths, the frequency is less than the threshold frequency, then no photoelectric emission will be there. If you see the frequency, this will be less than the frequency of the other wavelengths. So no photoelectric emission will be there. Then no stopping voltage is required to stop the current. Then we can calculate the slope. Slope AB by CB is equal to, substitute the values and it will be equal to H by E. So keeping H in this side, bring E to that side, from left hand side to right hand side. It will go in multiplication and substitute the values. You will get the answer as 6.573 into 10 to the power of minus 34 joule second. Then go for phi naught value. Phi naught is equal to H nu naught. Substitute the value of H and nu naught. Substitute the value of H and nu naught. You will get the answer as 3.286 into 10 to the power of minus 19 joules. Then convert it into electron volts by dividing it with 1.6 into 10 to the power of minus 19. You will get the answer as 2.05 for electron volts. So this is the work function. We have find out the threshold frequency. Threshold frequency value will be nu naught is equal to 5 into 10 to the power of 14 hertz, and then work function will be phi naught is equal to 2.05 for electron volts. Then we can go for 29 sum. The work function for the following metals: sodium, potassium, molybdenum and nickel. Which of the metals will not give photoelectric emission for a radiation of wavelength 3300 Armstrong units from helium-cadmium laser placed 1 meter away from the photocell? This laser is kept 1 meter away from the photocell. After some time, it is taken to the new position 50 centimeters. Okay, so molybdenum and nickel will not show photoelectric emission in both the cases. Lambda is equal to 3300 Armstrong units converted into meter, and then energy formula E is equal to Hc divided by lambda. Substitute the values, we will get the answer as 6 into 10 to the power of minus 19 joules. E is equal to, convert this into electron volts. So energy of incident radiation is greater than the work function of sodium and potassium only. So here the sodium and potassium energy are given as 2.75 electron volt sodium and 2.30 electron volt for potassium. Here the energy will be 3.158. So this is greater than that of the work function of sodium and potassium. If we compare with that of molybdenum and nickel, it is less with that of these two things. So this will not show any photoelectric emission. and if the photocell source of light is brought nearer to the photocells, means that is it is kept at 50 centimeters away from them, means the intensity of radiation will increase. If it comes closer to the source is coming closer to the for metal, it will the source will give high intensity of radiation. That is, the intensity of radiation will increase. This does not affect the energy of the radiation. However, the photoelectrons emitted from sodium and potassium will increase in proportion to the intensity. Okay, then we can go for the next sum. Light of intensity 10 to the power of minus 5 above meter inverse squared falls on a sodium photocell of surface area 2 centimeter squared. That is, intensity of light will be 10 to the power of minus 5 above meter inverse squared, and the surface area will be A is equal to 2 centimeter squared, and there are 5 layers of sodium absorb the incident energy. Top 5 layers are going to absorb the incident energy. Estimate the time required for photoelectric emission in the wave picture radiation. Then phi naught for the metal is given to be about 2 electron volt. What is the implication of your answer? What is the explanation of your answer? Intensity I is equal to 10 to the power of minus 5 Weber meter inverse square, and A is equal to 2 centimeter square converted into meter, means into 10 to the power of minus 4 meter square. Then power is equal to I into A. So substitute the values, you will get the answer as 2 into 10 to the power of minus 9 Weber. And then phi naught. To find phi naught, it is given as 2 electron volt converted into joules. 2 into 10 to 1.6 into 10 to the power of minus 19, it gives you 3.2 into 10 to the power of minus 19 joules. The layers, number of layers of sodium to be absorbed, the incident energy will be N is equal to 5. So the incident power is uniformly absorbed by all the electrons which are all present in the surface. So that E is equal to P by N dash is equal to 2 into 10 to the power of minus 26 joules per second. The answer is 2 into 10 to the power of minus 26 joules per second. Then we can go for the time period T. T is equal to phi naught divided by E is equal to, substitute the values, and you will get the answer as 1.6 into 10 to the power of 7 seconds. If this seconds is to be converted into years, means 0.507 years, that is half of the year. If the time required to emit a photoelectrons is half a year, means it is not possible, it is not be practical in the life. So the wave picture is in disagreement with the given experiments. Thus we have completed the 30th sum. Students, do fast and submit it.